Section modulus is a geometric property for a given cross-section used in the design of beams or flexural members. Other geometric properties used in design include area for tension, radius of gyration for compression, and moment of inertia for stiffness. Any relationship between these properties is highly dependent on the shape in question. Equations for the section moduli of common shapes are given below. There are two types of section moduli, the elastic section modulus and the plastic section modulus. Notation: North American and British Australian convention reversed the usage of S and Z. Elastic modulus is S in North America, but Z in Britain, Australia, and vice versa for the plastic modulus. Eurocode 3 resolves this by using W for both, but distinguishes between them by the use of subscripts, WL and WPL. Elastic section modulus: for general design, the elastic section modulus is used, applying up to the yield point for most metals and other common materials. The elastic section modulus is defined as S equals I/Y, where I is the second moment of area and Y is the distance from the neutral axis to any given fiber. It is often reported using Y equals C, where C is the distance from the neutral axis to the most extreme fiber, as seen in the table below. It is also often used to determine the yield moment such that μ equals SA, I florin Y, where I florin Y is the yield strength of the material. Plastic section modulus: the plastic section modulus is used for materials where plastic behavior is dominant. The majority of designs do not intentionally encounter this behavior. The plastic section modulus depends on the location of the plastic neutral axis. The PNA is defined as the axis that splits the cross-section such that the compression force from the area in compression equals the tension force from the area in tension. So, for sections with constant yielding stress, the area above and below the PNA will be equal, but for composite sections, this is not necessarily the case. The plastic section modulus is then the sum of the areas of the cross-section on each side of the PNA multiplied by the distance from the local centroids of the two areas to the PNA. The plastic section modulus is used to calculate the plastic moment, MP, or full capacity of a cross-section. The two terms are related by the yield strength of the material in question, phi, by MP equals phi Z. Sometimes Z and S are related by defining a K factor, which is something of an indication of capacity beyond first yield. K equals ZS, therefore for a rectangular section, K equals 1.5, use in structural engineering, though generally section modulus is calculated for the extreme tensile or compressive fibers in a bending beam. Often compression is the most critical case due to onset of flexural torsional buckling. Generally tensile extreme fibers have a higher allowable stress or capacity than compressive fibers. In the case of T-sections, if you have tensile fibers at the bottom of the T, they may still be more critical than the compressive fibers at the top due to a generally much larger distance from the neutral axis, so despite having a higher allowable, the elastic section modulus is also lower. In this case, FT buckling must still be assessed as the beam length and restraints may result in reduced compressive member bending allowable stress or capacity. There may also be a number of different critical cases that require consideration, such as there being different values for orthogonal and principal axes, and in the case of unequal angle sections in the principal axis there is a section modulus for each corner. For a conservative design, civil structural engineers are often concerned with the combination of the highest load and lowest elastic section modulus for a given section stationed along a beam, although if the loading is well understood you can take advantage of different section modulus for tension and compression to get more out of the design. For aeronautical and space applications where designs must be much less conservative for weight saving, structural testing is often required to ensure safety, as reliance on structural analysis alone is more difficult to justify. See also, beam theory, list of area moments of inertia, second moment of area, references. External links, http, www.engineeringtoolbox.com/ American-wide-flange-steel-beams-D_1318.html, list of section moduli for common beam shapes, http, www.novanumeric.com/ Samples.php $calc name equals section modulus, online calculation for section modulus.